Hello, everyone. I'll be talking about distribution network in the context of flexibility. I'm a research expert at Electa, and yeah, just to give it keep the discussion here introductory. I try to explain some of the basic things which makes it clear for other packages, like what does it mean when we talk about flexibility, what are the distribution network incidents we are talking about. So my presentation is divided into 5 parts. So I'll be talking about distribution network incidents, flexibility in power networks, behind the meter flexibility, what are the challenges associated with activation of flexibility, and lastly, which might be interesting for some of the teams here, is fairness aspects of flexibility. So distribution network incidents, when we talk about it, what exactly are they? So distribution network primarily composes of networks which supplies electricity to consumers. This consists of transformers, lines connecting from one node to the other, connecting the consumers, protection devices, and so entities that are involved here are distribution system operators, consumers, prosumers, aggregator, market operator, retailer. Of course, the list is not exhaustive, but these are key players in distribution networks. So, what exactly are distribution network incidents? They are primarily composed of uh, branch attributes. So, suppose this is a stylized picture that we often use for representing a distribution network. There is a secondary transformer which is connecting either single phase loads or three phase loads, and the line connecting from one node to the other can get overloaded. What does that mean? It means that the capacity of line has certain capability to carry current, and if it exceeds or touches that limit, we call it overloaded. So there are branch attributes which are related to currents, and then there are nodal attributes which are related to, say, voltages, unbalanced harmonics. So, for example, the node where they are connected, it's called the point of common coupling. And we can face some violations, power quality violations. So, just now I have introduced a new term which is power quality. What exactly it means? It can be classified in many ways. So, of course, in our context of our project, we'll be only looking at steady state and not the transient state. So, in steady state, it could be voltages, it could be nodal attributes, or it could be attributes related to the branches of the network. It can be divided based on the quantity, such as voltages, currents. So they can also have some attributes which are transient attributes that we will not be looking at within the framework of the project. It can be divided based on what voltage level we are considering. So within the project, we will be looking at, say, the medium voltage and the low voltage network. So both sides of the secondary transformer. What are the entities of interest for us? Are these generators, industrial consumers, or domestic prosumers? Of course, there are other entities which is not shown here. And then based on the load or supply. So these are a broad classification of like the power quality. European Commission also defines the power quality based on some standards, which is referred to as 50160. Of course, this table is not complete. What I wanted to show is these attributes have well-defined ranges, and different European countries can comply with these ranges either fully or partially. Within the framework of the project, we'll be looking at, say, sorry, so the voltage unbalance and the voltage magnitude violation. So this will be the key thing to look up. Of course, we'll try to also explore a little bit on harmonics, but I think it's not realistic to also cover that. So just now we looked at the European standards, but these standards vary from one country to other. So within complying with the European recommendations, it can be slightly tighter or looser depending on which region are we talking about. So more or less we'll be considering the European standard as our rule of thumb. So this section, we summarize that with the transition of power networks, the power quality metrics which are deteriorating needs to be considered. Distribution network incidents denote the incidents of power quality violations. For our case, it will be, say, voltage magnitude and line overloads and unbalances observed at either at the substation or at the point of common coupling of the loads. So DNIs are becoming more and more rampant. I'll be talking about in the next section, and they are becoming also very frequent, which is operationally a big problem for system operators to comply with and make sure that the system runs in a manner which is not compromising the reliability of the distribution network. Moving on to the next chapter, which is power network flexibility. What exactly is flexibility, and what is this flexibility for? So there are various motivations why we are talking about flexibility. First, I'll be talking about policies. So there are policies in, for example, I'll talk about the German 14A rule, which makes it possible for the grid operators to modify or correct flexible loads with a guaranteed minimum load of 4.2 kilowatt, which means that they can adjust uh, DERs. DERs includes electric vehicles, heat pumps, photovoltaic connections, and which can be adjusted or curtailed momentarily in a manner that it can avoid network issues. So the why this rule is important is because there are huge connection delays once you apply for a request to install a DER. So by this rule, the DSOs no longer is allowed to refuse or postpone the connection of these new assets due to insufficient capacity. So they can no longer make this excuse. Although it's not there as of now in most parts of Europe, but I think this is something that other countries will follow. In the US, they have FERC Order 222, which enables DER participation in energy markets, of course, at an aggregated level. But this still democratizes the participation of flexibility, which is distributed in the network for grid services. In Belgium, also we recently launched the local flexibility market, which is live from December 2024. Fluvius, along with Nodes, is running a short-term and long-term flexibility products, and this encompasses the policies. Now, from the second motivation is the load and the behavioral changes. For example, I'll give you two examples here. The EVs and heat pumps are growing at an exponential rate. So if we just look at 2021 to 2022, the increase in EV was 50% and heat pumps increased by 60%. Now, these loads have two big problems. They are having high peaks and they are simultaneous in nature. So, for example, the heat pumps they are strongly correlated with the external temperature, which means that when the temperature is low, all the heat pumps might be start working, which means they are coincident in nature, leading to network violations. So, we'll be testing the limits of the network because of these coincident loads. Next is power network volatility, which is leading to connection delays. I think everyone is giving this example of Netherlands, where you can see this is a map of December 2024, where you can see the traffic light indicators of the connection delays. So red is the region where there is shortage of capacity. So any incoming capacity will have huge delays. Possibly the network needs to be upgraded. So this is for the transmission, and that the adjacent one is for distribution networks. Uh, Distribution network is still not yet as worse as the transmission, but I think with the increase of distributed energy resources, is going to follow the track. So these are three key motivations. Now, what exactly is flexibility that we are talking about? It's the technical ability of the power system unit to modulate power, either positive or negative, both for active and reactive power. So ENSO-E defines power system flexibility as the ability of the power system to effectively manage variability and uncertainty of electricity demand, supply, and grid availability. So these are the three sources of uncertainty that they have identified across a range of timescales. So we are talking about a multi-period operation, which makes it optimization sense-wise more difficult. Um, So the goal of flexibility, as defined by ACE, which is a lobby organization for energy storage devices in Europe, they use the same objective for using flexibility as EXOE. Now, oftentimes in practice, the deviation from a business as usual is defined as flexibility, which means that we are talking about a baseline. So I'll be talking about a baseline. What exactly is this baseline? Um, but before that, let's summarize the key importances of flexibility. It increases and helps us increase the DER penetration. They are active elements, so system operators can use them to mitigate network issues. Uh, Flexibility facilitates more effective use of the grid, so the distribution network assets can have a better utilization because of uses of flexibility. Flexibility owners can have financial incentives. So, of course, these incentives promote them to operate in a manner which can help them reduce their electricity consumption bills while also not compromising on the quality of service that they receive. So, how to quantify flexibility? Flexibility is typically quantified based on these five key metrics related to active and reactive power. Now, how does that look like? It's a three-dimensional space that we are talking about, which has for active power, which has the power, the ramp rate, and the energy. Now, this is a simplified notation of flexibility in three dimensions. Of course, it's more complicated. And reactive power does not have the energy component to it because an inverter which is interfacing a DER has a capability which is linked for active supplying both active and reactive power. I will not go in detail. So the lack of energy component is because reactive power is often supplied from the converters or inverters based on the spare capacity that is used for active power. So there is no energy component for reactive power here. How do we model flexibility? So coming back to the baseline, so there is one way of baseline. I'll be talking in optimization wise because I think it's more intuitive. So let's say we have a deadline constraint, an electric vehicle arrives, and we want to charge the electric vehicle up to a level. Now we have some operational constraint like how fast that charging can happen, and what is the ramp rate that can happen. So and how much energy. Deadline constraint is the energy that the device should consume for that horizon. So I'll demonstrate that with an example. Let's say the electric vehicle arrived at 6 in the morning and the vehicle stayed there till 6 p.m. in the evening. So 12 hours of connection time. But the charging time was only from 6 to 12, which is 6 hours of charging. So typically, what happens is the vehicle came and it started charging almost immediately, and it consumed the desired amount of energy at half the time, and for remaining half, it remained idle. So it was doing nothing. So if we do an energy management, say there is a price variation happening, and based on that price variation, we can redraw the trajectory, which is shown here in the second plot. Now, suppose we add more constraints to this optimization, such as now my ramp rate cannot increase all of a sudden. Now, what does ramp rate means is I cannot charge my battery all of a sudden to 0 to 11 kilowatt. It has to go in steps because that reduces the stress in the battery, or there is capability associated with the storage that does not allow you to ramp very fast. In that case, we have a new trajectory which has a ramp rate of just 10% capable with respect to the Pmax. What we show here is with this ramp rate constraint, the amount of financial gains that the customer did not make was less than 10%. So that was quite amazing because although for batteries it's not a concern, but a lot of these flexible devices have ramp rate constraint associated with it. Flexibility quantification is often performed using a baseline, as mentioned previously. With respect to the baseline, this ramping up or down is calculated. So, what exactly is this baseline? Let's assume we have a historical average shown here in the dotted line, and the blue curve is the actual load. Now, the deviation with respect to the baseline is what is assumed to be flexible. Now, this is very contentious discussion because the baseline in itself is not right obvious. So there are many methods in literature which uses like historical baselines, model based, moving average, day ahead. They use just the forecast as a baseline, but it's very hard to quantify actually in reality because each consumer will have their own way of uh, consumption, and that might not be similar or depend on the historical profiles. So if not baselines, then what? So baselines may not be useful for, say, continuous operation of distributed energy resources. So the alternate classification that we come up with, we divide the flexibility based on the flexibility availability, which is say explicit or implicit. Explicit implying the amount of flexibility is well defined, implicit not well defined. Flexibility management, it can be direct or indirect. So just to look at some of the examples which is happening all over the world and where do they fall in this two-dimensional plane. So this is a two-dimensional plane in which we have flexibility availability on the x-axis and management on the y-axis. So let's call type 1 flexibility, which can be explicit and direct. And this is what the Germans are doing within 14A framework, where there is direct load control, dimming of the loads, in order to minimize network incidents and perform some sort of active network management. So this is an intrusive method in which the control signals are either generated directly from the centralized location or can also be decentralized. Type 2 is, for example, in Australia. So they have a dynamic operating envelope sent to the consumers, and within these ranges, the flexibility should be operating. Type 3 could be local flexibility market. So we don't know how much flexibility is there. So it's an implicit price-based demand response could be an example of this method. And lastly, type 4, in which the amount of flexibility is known. For example, contractual agreement with the aggregator in which they have to respond when an incident happened, or a local energy storage. So then there are some devices such as OLTC, voltage regulators, and capacitor banks, which can also provide some sort of flexibility, and they are explicit, but they can be direct or indirect. They can have a centralized signal commanding them what exactly to do, or there could be an indirect method. Just to summarize this section, flexibility is crucial for economically viable network operation with large scale integration of intermittent renewable energy sources or other DERs. The flexibility are heterogeneous in nature, which can be classified based on the availability and management, and can be quantified based on the power, energy, and ramp rate capabilities. So model for flexibility can be with or without baseline. So of course, within the framework of the project, we have to look which of these methods we'll be considering. Moving to the next section, behind the meter resources. So these are large, small scale resources which can deviate based because they have some sort of temporal flexibility. So what do we exactly mean by behind the meter flexibility? So these are, as I mentioned, temporal flexibility, which has shiftable loads such as water heaters, building HVACs, electric vehicles, and so on, and they can deviate based on whatever their local objective is. So there is a local objective and there is the network objective, and we'll be talking about it subsequently. So the local objective is to minimize the cost of electricity and possibly through maximizing self-consumption. They want to also maximize their own preferences or comfort. For example, in HVAC, you want the temperature set point to be not oscillating in a wide band of flexibility, but a small band might be not noticeable of 1 or 2 degrees. So when we talk about the grid constraints, the optimization for distributed behind the meter resources become a multi-objective optimization, which has certain local grid constraints, such as grid constraints, local constraints associated to the devices, and their own objectives. So this is a bit not trivial. Now, how do we consider the grid? So consideration of the grid could be an indirect one or a direct one. Indirect means includes applications such as demand response, which are event based possibly, to reduce power consumption during peak demand. Or it could be direct load control or direct grid considerations such as centralized dispatch of flexibility, such as what Germany is doing. And we can categorize the network consideration with this flow chart. So it could be indirect. Indirect could be subsequently passive. Passive means the amount of flexibility is not clear; it's implicit. And the grid consideration are through, say, time of use prices or demand response signals. So they are not a direct representation of the grid, but they do represent the grid. Yeah. Or peak demand charges that we also have in Belgium. Similarly, for active, it could be voltage sensitivity factors. So these could be time varying sensitivity coefficients, or could be static, or PTDFs. So these are replicating the actual AC power flow. And for the direct one, it could be approximate or exact. So the approximate could be decentralized and centralized and distributed, and exact could be centralized, which is a direct load control. Um, so just to summarize this section, behind the meter resource consists of diverse sources collectively referred as DERs. DERs have local objectives of quality of service, preference, deadline, and comfort. In the grid, consideration of operating distributed flexibility is crucial for ensuring operational integrity of distribution network with large penetration of DERs. With this, we'll move to the next. If anyone of you have questions, I'll pause for a bit.
I have one, but I can continue after the presentation because it relates to something you mentioned on fairness and.
I'll come to fairness.
Okay, great. I'll show.
Yeah, because I know that many of you are interested in the fairness aspect of it, but we already have a notion how we look at fairness. But of course, you might bring a lot more things to that. But yeah, that's the last section I'll be talking about. Now, when we talk about activating flexibility, so till now we assumed that all the flexibility will be activated by itself, but that's not how it's going to happen. So there will be a lot of other bottlenecks such as communication and information exchange. So this section will cover that part. So as mentioned, the activation of flexibility is can be fragmented into multiple problems. So say the first part is measurement and forecast. Possibly state estimation could also be part of this, in which we try to assume the network's state based on real measurements or forecasted or state estimation. And then we look into the communication aspect, like how much information can be exchanged. Can Is it capable to two-way communication? Is Are there delays in the network communication? So I think these will affect like at how fast can we operate those resources. And lastly, who is making the dispatch decision? Is it at the centralized level, decentralized level, or distributed? So since we also have some task within the framework of Flex IQ, in which we'll be talking about comparison of these different architectures, I'll be briefly describing that. So just before we move ahead, if we look at the continent of Europe, the smart metering landscape and the capability these smart meters have has huge disparity. Just to handpick two places, Netherlands and Spain, which has 100% penetration of second generation smart meters, which can have two-way communication, compared to Germany, where it's almost showing 0%, but it's not actually zero because this report it was 2018, so already 6 or 7 years. We might have an update of this, but the point to make here is there is huge disparity among even continent of Europe, where the smart meter capability is not uniform. Just to keep that in mind. So these the penetration level has variation. The amount of what kind of communication that they use has disparity. Thus, the capability of smart meters are very different. So we have to make a case by case evaluation for such situation. Just to go back to our previous diagram of the two dimensions of flexibility, availability, and management, if we try to look into like how much communication needs will be required for these dimensions, So for type 1 flexibility, which was direct and explicit, in which we were talking about direct load control. So this is exhaustive in the amount of amount of communication needs. So the activation signal has to be sent. They should be capable of two-way communication, and it has to have low latency. For type 2 flexibility, in which we are talking about dynamic operating envelopes, the activation signal is sent, but the dispatch decision is not made from the central level. So the consumers are still making their choices within those operating envelopes. So type 3 is like a market price signal has to be sent, and then they should be capable to receive that and respond to that. So there is a home energy management system kind of a device at the consumer side. And the last one, which is independent, so they should have a monitoring and control capacity at the connection point. Flexibility activation feedback should be provided at the central level, and again there is a decentralized decision making box, which is the home energy management system. Not talking about these devices because mostly they are owned by the system operator, so they are frequently dispatched centrally. Just to give clarity so that all of us are in the same page, so decentralized control has notionally different definitions for in the control and in optimization circles. So when we say decentralized, we mean there is no information exchange. There is no central server exchange, no communication needs. And when we talk about centralized, we of course it's quite clear what it means. So all the information is exchanged to the central server. The decision is made at the central level, and the dispatch decisions are coming from the central level. But the decentralized one, because I think there is some confusion between what do we call distributed and what do we call decentralized. In computer science, decentralized does not actually mean no communication, but here we take the control definition of decentralized. So just to give an example, like how will the decentralized control look like? So consider the voltage measurement as the coordination signal, and based on this coordination signal, we generate some operating envelopes, and within these envelopes, we define these resources. So the shortcoming, of course, for this is that you cannot respond to power quality violations happening somewhere else in the network. So this is of course the obvious one, and the network violation other than or for other metrics, other power quality metrics that we are not measuring, it's not possible to be compensated. An example, which is a paper that we completed yet not submitted, is let's say there is a traffic light signal. So this is the red, green, and this is the red, yellow, and green, and we want to be in the green range. So this was the nominal behavior of the load when there was no response or no awareness for the distributed resources to operate. And the red is the corrective line. So you can say that at the decentralized manner, we were able to compensate for all the violations happening within that node. But if there were violations happening some other places, those resources cannot respond to that. With this, I'll summarize this section. Flexibility operation is a combination of several problems. Of course, communication, measurement, and grid compliance needs, which can also vary from one country to other. And centralized versus decentralized operation of flexibility. So there are local grid constraints, local objectives of the devices, and then there are grid constraints associated with power quality and probable distribution network incidents. I'll jump into the last section, which I think a lot of you are interested in. So, notions of fairness. Can everyone be a winner? Of course not. Uh, it's a very complicated problem. A lot of people say,
You should ask, is everyone an equal loser? If everyone a winner, we know that doesn't work. But if everyone is an equal loser, then
yeah, we don't want everyone to be a loser too. We'll see. Like, so many people say power networks are the most complicated system that human beings have ever made. So you have so many entities, and we have made it even more complicated with new entities such as BRPs and policymakers and regulators who are the stakeholders, and everyone has their own goals in the system. Of course, within the frame of the project, we'll not be talking about all these entities. We'll be focusing only on the distribution side of the power networks, and but they have many different goals, and you can get the flavor. So I listed three of the goals here. So let's say the system operator's goal is to operate the system reliably. So there are no power quality violations. They don't want any obstruction in the operation of the network. Then you have the stakeholders, such as consumers. They want to maximize their own profits or minimize their cost of consumption. And then the third aspect, which is very important to look into, is the societal aspect. Like, what is the social welfare? And I will demonstrate what do I mean by social welfare. Maybe within your perspective, it might vary. And then there could be n number of goals that we are not aware of, and that might come here based on what stakeholders are we considering. So, what are the notions of fairness? I think most of you are aware of it. Utilitarian and egalitarian. So these are two extremes. I think extreme notions for fairness, and there could be a bunch of different methods in between utilitarian and egalitarian, such as bounded opportunity, proportional fairness, and so on. It is difficult to describe this notion of social welfare because it highly depends on what stakeholders are we considering in our problem. There are a bunch of inequality metrics. I'll not be talking about them. So typically, we use Gini index and Jan index a lot, but then from optimization sense wise, we also look for something called convex. So alpha fairness and proportional fairness are also highly used. So for the people who are not aware of flexibility, I'll just give you an example of how Gini index is calculated. So you have the cumulative, let's say we are talking about hosting capacity. Now, there are 100 people connected to a feeder. Each one can have certain amount of DGs connected to them, and we calculate the hosting capacity. And we were never maximizing, we were only maximizing the amount of distributed generation connected to the network, and we then sort those DGs connected and draw a curve. Like, so if we take the tail end of the how many whoever had the minimum amount of DGs connected, so this will have a curve like this, and this curve is called Doran's curve. And ideally, everyone should have equal amount of DG, but that's not going to happen because of how the distribution networks are designed. Now, the distance between this is, or the area, the ratio of this area A and upon the total area of the triangle is what is called Gini index. So this inequality, as we expect it to be substantially high for distribution networks because of how the networks are designed. I want to show our notions of fairness with an example. So let's say we are trying to maximize the how much amount of PV that can be connected in a feeder. So let's say this is the amount of PV that can be connected at a particular node, and we just sum up, and we don't care how much PV is connected at one particular node. Now, this problem will look like something like this, plus some sort of fairness objectives, and we will try to show how those objectives look like. So, for utilitarian, we want to maximize the social welfare. We want to maximize the amount of DERs that are connected in the network. So we just sum up all the DERs. So that's our first objective. The second is, and let's look at the egalitarian, because I think these two are extreme and everything in between is some sort of a bargain between egalitarian and utilitarian. And egalitarian, we want to just maximize a value of DG, which is equal for all the nodes. We don't care how much they are consuming, we don't care what is the connection, and everyone has the same. So the amount of disparity here is minimum. The amount of disparity here could be very high, not necessarily. And then we have two metrics. The efficiency metric is to compare how much amount of what is the price of fairness. So this is again a standard term which is used in this literature. And then there are inequality metrics. We can have the largest disparity or the Gini coefficient. Uh, so this is how we look at fairness. This is our notion of fairness, which may vary because social welfare is not something well defined. We want to also look into the equitable opportunity versus fairness metrics. Is crucial for power networks managed by DSOs that operate as a oligopoly. So it's almost like a there are there is no competition within a region because each region has a DSO. I'll try to summarize all the key takeaways. So we had 5 sections. In the first section, we talked about distribution network incidents. So what are power quality violations? And because of large amount of DERs that are connected in the network, these networks are becoming more prone to violations. Then flexibility in power networks. The need for flexibility is growing, and its quantification is not yet clear. So there is a lot of room for innovation there. Behind the meter flexibility, finding a compromise between local objectives and the grid objectives is absolutely crucial. Activation of flexibility is a challenge and is a multidimensional problem again, because it requires information exchange, communication needs associated and quantified with it. And then finally, I talked about flexibility, which is equitable opportunity for all stakeholders versus social welfare maximization. That's it. Thank you for the attention.